thank you, Elena, for the introduction. And yeah, I really want to thank the organizers for not only inviting me, but also letting me give this talk without taking any risk crossing back and forth the US borders. So today, well, I'm going to talk about two aspects of chiral phononics. And I will also talk about it, trying to give you an introduction, but also in the context of some works. The first of these works were done with Alan McDonald during my postdoc. And then more recently, we have some new results together with my PhD student, Rule, and Violet. So before going into the details of these works, I also want to really clarify which type of chiral phonons I'm talking about. So as you all know, this word, chirality, that has been really borrowed from the field of biology, has been used very liberal in the context of phononics. So I'm going to still use it very liberally, and I'm really going to talk about, in some sense, the least chiral phonons that you can think of. But I just want to really make clear the type of phonons that I'm going to address. So while certain things that I will be discussing can also be applied to optical phonons, what is really my main focus are acoustic phonons. So that, at least in my opinions, are the phonons that we have been less thinking about of as chirals. And I'm going also to discuss these phonons mainly in the context of 2D phenomena. So when I'm talking about these chiral phonons, I'm thinking about simply some acoustic phonons that can be described by this equation. So they are nothing but the eigenmodes of this eigenvalue equation, where here we have a dynamical matrix. And if you think about the most general form of a dynamical matrix that you can write in a 2D system, the one that you will come with looks like this. So here there are these first two terms, and if you combine them together, as I will show you, they give you just really the usual dispersion of a 2D acoustic phononic system, meaning a transverse and a longitudinal acoustic phonon. Then, if you want, you can start thinking about the terms that can be generated by breaking inversion symmetry. And then there is this term that I will discuss in more details in the next slide. But what I really want to make clear is that the truly chiral phonons, the one that come from structural chirality, and therefore require inversion symmetry breaking and possibly even chiral or polar materials, are really not the focus of these talks. So there have been a lot of really interesting experiments in which they have been visualized, for example, in quartz. But they will not be the ones that I will be discussing today. So removing that term, the system that I'm addressing, and I'm going to talk about, it's even simpler. So if you think about it in terms of a dynamical matrix and therefore simple equation of motion, these are the terms that I'm going to keep in this discussion. And one term that is definitely very interesting and has been addressed in different contexts is this final term. It's this final term. So it might look like a non-Hermitian term, right? Because you see here the emergence of this imaginary unit, but actually it's something that is really analogous, as I will show you, to a Lorentz force, and indeed, in the context of transport, has been named dissipationless phononal viscosity. So in order to have this term, you need to break the time reversal symmetry of the phononic system, and specifically the time reversal symmetry in this case of acoustic phonons. So how you can do such a thing will be really a main part of this talk. And also, I will try to address something that, somehow it's subtle, especially if you haven't been working a lot in the context of transport and thermal Hall effects. So when time reversal symmetry is broken, as probably most of you know, phonons are just allowed by symmetry to inherit a net angular momentum. So time reversal symmetry will have this effect when it's broken, and it will endow the system with an intrinsic chirality. But also importantly, we know that when time reversal symmetry is broken, we can have a whole type of effects. But here the subtlety is that this does not necessarily require an intrinsic chirality. Not all effects have to be intrinsic. Simply Onsager dictates that when we are working in linear response, some Hall effects are allowed by symmetry. So I will really put the main focus of this talk in discussing, the recent measurements of giant thermal Hall conductivities that have been observed in several dielectric oxides. And then I will go through all the mechanisms that can possibly underline a phonon-driven thermal Hall effects. And I will try to answer, though I don't think I will be able to offer a complete final answer. I will try to answer the question of whether thermal Hall responses imply an intrinsic phonon chirality or not. So if we observe a giant thermal Hall effects due to phonons, can we also think about these phonons as chiral phonons having a phonon angular momentum? Then before I start going into the details of that, let me also just give you a preview of the second part of this talk. So in the second part of this talk, I will address a system that it's even simpler. I would say it's the most boring type of phonons that you can think of. So I will neglect this term that would be the central part of the central part of this talk. I will suddenly neglect it. I will assume that neither inversion symmetry or time reversal symmetry are broken, and I will consider a 2D phononic system in which you have two phonon eigenmodes, a longitudinal acoustic and a transverse acoustic mode. And as we think of these modes, I mean, at least as I was thinking about these modes until very recently, has been modes that have no sense of chirality whatsoever, right? They are linearly polarized. There is no mechanism that can endow them with any chirality. And from a symmetry standpoint, there is PT symmetry in such a system. So whoever of you has been working with the phonon angular momentum knows very well that in this case, phonons cannot generate a net angular momentum, but also at the level of individual modes, they cannot have any angular momentum at all. However, I will show you that what we recently found is that even in this type of system, there are finite angular momentum fluctuations, and I will really try to clarify what I mean with this. And even more surprisingly, this finite angular momentum fluctuations survive even at zero temperature, or if you want, in the phononic vacuum. And they seem, at least to us, to represent a really novel in some sense, because it's purely collective type of vacuum noise. And I will also discuss how we can experimentally access these vacuum effects, and also possibly some connections with some phonon transport phenomena that were revealed in this work already 5 years ago. So let me first start with the first part of this talk, and I will try to review historically how all this interest in chiral phonons from the point of view of transport got revived in the last 5 years. So at least from my perspective, as I was working on this during my postdoc, it all started with this experiment in the group of Louis Taillefer, and here the first author is Gael. So what they found was that there was a giant thermal Hall signal in the pseudo-gap phase of cuprate superconductors. So namely, as you start entering in the pseudo-gap phase, you start measuring a quite strong thermal Hall effect. Now, strong means that is 3 or 2 order of magnitude smaller than the longitudinal conductivity. And even more surprisingly, this effect was becoming even stronger when you were deep inside the insulating phase. So already this experimental observation suggested that here the carriers cannot really be electrons, right? This signal is the strongest in the insulating phase. So it can definitely not be attributed to electrons. So what just naturally came after was an exploration from the same group about the role of magnons. So generally in these high temperature superconductors, there have been many theories suggesting that the presence of long range or short range type of specific antiferromagnetic correlation can be, a driving force in the emergence of this unconventional superconductivity. And therefore, naturally, they went on and they tried to explore if this type of magnetic fluctuations could also be responsible for this thermal Hall signal. And here, for example, in this plot, so what I'm showing is that they try to apply magnetic fields that would affect the magnetic order, eventually break also some symmetries or open, or even modify the gap of the antiferromagnetic excitation, but they didn't see really any substantial difference. And something that was even more revealing was the fact that it's very well known that magnons in this type of materials are very anisotropic, meaning that their dispersion is very different when considering motion in the 2D planes with respect to the autoplane direction, while instead phonons are very isotropic. So they really smartly changed the configuration of their experiment, and they saw that these thermal Hall signals were extremely isotropic, suggesting that magnons mostly or spin fluctuations were not really involved. And another, even I would say, stronger confirmation was this result from the group of Benya. So they also reported, actually, in the same year or next year, but just 6 months later, they reported a very strong giant thermal Hall signal in strontium titanate, which is a material that has no magnetic order. So another indication that phonons might be the ones involved in generating these giant thermal Hall signals is the similarity between the temperature dependence of the thermal Hall signal with the longitudinal thermal conductivity. So as you can see, the shape of these two is not identical, but it's very similar. And in this type of material, it's been quite well understood that the longitudinal conductivity or the longitudinal thermal conductivity can be described in terms of phonon process, and especially in this range of temperature, what plays a very important role is scattering over defects. And this will become important later on. But as you can see, this signal is mostly peaked where in that same range of temperature that in which Rayleigh scattering dominates longitudinal transport. So after this experiment of Benya, there have been really a flurry of other reports of giant thermal Hall conductivity in many dielectric oxides, and even more recently in materials that are not dielectric oxides. So as you can see, just I think 2 years ago, there was a table being compiled, and at that point, these were the materials that displayed giant thermal Hall conductivity, and even more are coming out right now. So clearly, this phenomena seem to have not much to do with the unconventional superconducting nature of for example, titanium cuprate, and it really triggered, I would say, in the community a question that it's very fundamental. So here we are looking at transport, and we are looking at transport at very low temperatures. So definitely the main carriers of it are acoustic phonons. They cannot be, because of the temperature range, optical phonons. So then the question that really comes about is what allows acoustic phonons to couple to magnetic fields. And generally, what we need to identify in order to answer this question is a time reversal symmetry breaking mechanism for the acoustic phononic system. So during that time, there have been a lot of works in this respect, and since I cannot go over all of them, allow me to divide them really into main categories. So there are several works that have identified some time reversal symmetry breaking mechanism that is within the phononic system. So I will call it intrinsic. And what I mean with intrinsic is that this time reversal symmetry breaking mechanism really comes about as a coupling term into the Hamiltonian. And is generally a coupling of acoustic phonon to a degree of freedom that in turn can couple to the magnetic field. And there have been several degrees of freedom that have been invoked in this respect. For example, electronic states or exotic electronic states, polarization or magnetization. And then there is a completely different category of proposals that have identified instead the time reversal symmetry breaking mechanism in the scatterers. So it's really an extrinsic mechanism, meaning that you can write, as I will show you, a theory for very boring phonons, ignoring any type of, for example, angular momentum that they carry, and you can still identify some strong Hall effects in the moment in which you consider specific scattering mechanism on certain impurities. So I will start first with reviewing the intrinsic time reversal symmetry breaking mechanism. So once again, what I find very useful is to think about this problem from the point of view of symmetries, right? You need, in order to have a net Phonon angular momentum, and in this case, really the main focus is a net intrinsic thermal Hall effect, you need to break time reversal symmetry. And in order to break time reversal symmetry, you need to find a way to couple acoustic phonons to the magnetic field. Now, assuming that you have been capable of doing that, a very convenient way to write this theory is from the point of view of is in terms of this action, and in this action. For phonons, if you have broken time reversal symmetry, you will get a term that looks like this. So it's called dissipationless Hall viscosity, and for whoever is not familiar with this term, it's really a concept that has been borrowed from quantum Hall physics. So it appears really in the equation of motion, as you can see here, as a Lorentz force that in this case is dependent on the wave vector. So when looking at the source of the intrinsic mechanism, at the time in which we started looking at this problem, we noticed that there were already many proposals. So Magnus, for example, has already mentioned electric polarization or quantized anomalous Hall states, spinons. There were really several works possibly identifying a mechanism that could endow phonons in the system of intrinsic chirality. Now, the issue is that all these works are absolutely valid, but when you talk about magnons, you are obviously identifying this mechanism only in magnetic materials. And if you just remember the table that I've shown you, some of the materials in that table were magnetic, some other are not. And you could apply the same principle for all these different proposals. So I would say one of the first questions that we ask is whether also boring ionic insulators with no magnetism, no ferroelectricity, or no non-trivial electronic topology can have a finite Hall viscosity. And there have been definitely several works that have addressed how optical phonons in these materials can couple to electromagnetic fields. But here the question that we are really asking is whether acoustic phonons can do so. So I will just give you a, hopefully very simple overview of the type of theory that we wrote. We consider the simplest system ever, so a bipartite ionic crystal lattice in 2D that is subjected to a magnetic field out of plane. And then first we did ignore the magnetic field. We just wrote down the equation of motion of this system, and we found that it was very convenient to rewrite the system in terms of the in-phase and out-of-phase motion. So nothing but the eigenvectors of this matrix at the gamma point. So if you think about these eigenvectors, they're literally the in-phase and out-of-phase motion of the atoms. And then, of course, when you include elastic interactions, as you well know, this elastic interaction will couple these two systems. And then if you diagonalize that matrix, you get your proper acoustic and optical phonons. Now, what is important here is that the out-of-phase motion of cation and anions will feel a Lorentz force, and this is not, a news at all. If you have some ionic crystal and you have different charges, the Lorentz force that is acting on the out-of-phase motion does not cancel out, but it will definitely cancel out for the in-phase phonon modes. Now, if you continue writing this theory, you realize, though, that if the out-of-phase modes are coupling to the magnetic field, and in turn they are coupling at least at the finite wave vector to the acoustic phonon, they actually provide, they become now the intermediate degrees of freedom that is mediating the time reversal symmetry breaking between the acoustic phonons and the magnetic field. And so for us, this was a demonstration that there are no degrees of freedoms other than the phononic ones that are needed, at least in this dielectric oxide material, in order to have some intrinsic chirality and possibly some intrinsic thermal Hall effects. So I will maybe skip some of these details, but writing the theory was very simple. We will just at this point plug back in the effect of the Lorentz force, and if you integrate out the out-of-phase modes, what you find are this simple equation of motion. So you can see that even in a very generic ionic crystal, the acoustic phonon, even if so weakly, can couple to the magnetic field. So then we ask the question of how weak is this coupling. So we try to make some estimates, though not being DFT theory people. So there we will say some approximative estimates, and we saw that the dissipation Hall viscosity that one could predict just due to the ionic nature of a crystal is comparable, if not larger, to many other dissipation Hall viscosity that were reported and attributed to more sophisticated mechanism. Now the question is, does this mechanism really explain the giant thermal Hall effects that have been observed? So I will say that most likely the answer at this point is no. One first indication was this theory from Gu and Sachdev, in which they really asked the question of if I have a generic acoustic phononic system with an Hall viscosity and I write down a Boltzmann transport theory. Now, I will definitely get, just by symmetry, a thermal Hall effect. But will this thermal Hall effect really scale with temperature as what I observe in the experiment? So maybe I would remark that this is the only work that addressed really this question. But assuming that everything is consistent, the results are really telling you that the scaling between the temperature dependence on the longitudinal and thermal conductivity will be very different. And therefore, while this effect might be there, it's probably very weak and is not what explained the experiments. And even more recently, I think just this last year, there have been reports of giant thermal Hall signals in non-ionic crystals in which this mechanism cannot really take place. So then the question is still, what it still remains? What does really break time reversal symmetry in crystals, and why there are these giant thermal Hall effects? Why are they showing up across materials that are extremely different? So I think that then the natural question to ask is whether what is at play is not an intrinsic mechanism, but rather an extrinsic mechanism, meaning that independently of the characteristic of the phononic system itself, they are scattering on certain type of impurities that are very common across different type of materials. Could be the one thing that really the mechanism that is underlying this experimental observation. So we looked first at this hypothesis, and actually this was our first work. We looked later at the intrinsic mechanism, and what the theory that we put together, it's really based on quite simple experimental observation. So the thermal Hall signal that have been observed are particularly pronounced around this temperature range. And it's very well known that in the temperature range, the longitudinal conductivity can be explained in terms of scattering on defects. Now we are talking about quite low temperatures, so very long wavelength acoustic phonons, and this allows to treat this problem in the so-called regime of Rayleigh scattering, which simplifies already a lot the calculation that otherwise would be really cumbersome. And at that time, we had to think about the type of defects that could imprint a sense of time reversal symmetry breaking on the phonons, and the defects that we thought of were oxygen vacancies, because what was mainly reported at the time were giant thermal Hall signals in dielectric oxides. So here the idea is that there is an acoustic wave, say longitudinal, since they seem to longitudinal acoustic phonons are the main contributors to thermal transport in this low temperature regime. And now these acoustic phonons, independently of their intrinsic nature, are scattering acoustically on defects, but defects can also be locally unscreened, right? This happens especially in dielectric oxides, and this also happens as sometimes there is an accumulation of charges at an interface rather than another. So then we have to write down a theory for this, and maybe I will just go through some main points just to give you, if you haven't done it before, an idea of how to look at this type of theories in which the mechanism is really extrinsic. So what we did was to look at a Boltzmann equation that describes phonon transport and is well known to describe well phonon transport when looking at the longitudinal one. And then here, the quantity that really plays an important role is the scattering rate. And we did this by borrowing, I would say, at the time, all the knowledge of my ex-supervisor on similar problems in the context of electronic systems. So in order to have some Hall signals, what you need is some skew scattering. There are other possibilities, but skew scattering is definitely something that will enable you to have a thermal conductivity. Now, the skew scattering term is this one, and what really became our job was to identify lambda. So, was to identify really what enters in this coefficient in order to give us a non-zero skew phonon scattering. So we model the system as, again, long wavelength phonons that are experiencing two types of perturbation. So the first one is very well known, and it's really a scattering problem in spherical harmonic waves. So it's acoustic scattering, and we specifically model this acoustic scattering, also accounting for some viscosity inside the defect. So the longitudinal acoustic phonons are impinging on the defect, they scatter, and they also lose some of their energy doing so. And then importantly, and really key to this model, is the idea that as the waves are propagating close to these defects that are partially unscreened, they also perceive a Lorentz potential. So they feel locally a Lorentz force. And we assume that this process is going on with an ensemble of random impurities. And differently from other proposals that followed after ours, we also do not attribute to this impurity any special type of correlation. They're just random oxygen vacancies or other type of impurities that are unscreened, distributed in the system. So there are a lot of calculations that go into that, but ultimately what we derived is a scattering rate via the Fermi-Golden rule. And these components are what describe acoustic scattering. So here you see two components. One is, let's say, the emission, the energy conserving part of this acoustic scattering process. And then very importantly, there is also a part that encodes attenuation of the waves. And here you have a very simple Lorentz force. Now what we found is that if you put all these ingredients together, you can get a scattering rate that is linear in the magnetic field. And perhaps not yet fully clear, though we are working on it and some possible connection to other field. It's essential to this proposal to account for inelastic scattering. So you don't need only the Lorentz force, you also need some loss in the system. What you derive at the end is something that doesn't look very pretty. It's this scattering coefficient that, as you can see, is very model dependent. And here our model is very, very simple. It's just a continuum model for acoustic phonons. And also importantly, if you look at this expression, you will see that it can change sign depending on the parameters of the system, which in turn can be temperature dependent. And this is also something that was observed experimentally. But it's very hard at the level of a continuum theory to exactly predict where the sign change will occur. So the best that we could do at that point was to provide a simple estimate of this coefficient, and we found that within reasonable parameters we could predict the size, the relative size of the thermal load signal versus the longitudinal conductivity. And I think even more importantly, we were able to plug this back in to our Boltzmann theory and really look at curves that would be generated due to this skew scattering. So here we took the data from this paper in which they reported a giant thermal load signal in this antiferromagnetic insulator. And as you can see, our theory can predict quite well not only the relative magnitude, but also the temperature dependence of the effect. So this is our fit for the longitudinal versus thermal Hall conductivity. So maybe coming to the conclusion of this first part, I would say that the main messages are that a finite Phonon Hall viscosity can be present in a ionic crystal without having to invoke coupling to other degrees of freedom or any exotic electronic state. But I would say that most likely this is not really the mechanism that is driving the size of the thermal Hall effects that have been observed. And at least in my opinion, most likely this mechanism has some, at least, maybe not completely, but at least some extrinsic origin. So it's essential to consider scattering on impurities. And even maybe more interesting, there's been this recent reports of a universal phonon thermal Hall effect in crystal. So here the authors, I think this is just from, I think from the beginning of this appeared at the beginning of this year. Here the authors not only reproduced many of the observations that were reported in the last 5 years, but they also consider very simple system, so silicon and germanium, and they show that even in this type of materials, one can record a giant phonon thermal Hall effect. So I would still say that but feel free to contradict me, while the community is really converging towards the idea that there is an intrinsic mechanism at the heart of this phenomenon, there is still quite some debate going on, and is in some sense still an open puzzle, if any one of you is interested in looking at that. So with this, let me completely switch gear and talk about what I initially called the most boring type of phonons, and the presence of finite angular momentum fluctuations in this system. So this is the operator that I define as the phonon angular momentum operator. Notice I'm just taking the Z component because I'm really considering a simple 2D system. So it's the only one that will be allowed. And I will look at this quantity. Well, my PhD student will really look at this quantity and try to calculate it in a system that has asymmetry, meaning in a system in which neither individual phonon mode can have angular momentum, or where there is not even, and then definitely there is also obviously not a net phonon angular momentum. So while we also generalize this to 3D systems, let me present it maybe in the simplest way possible by considering a 2D crystal with two non-degenerate phonon modes. Time and inversion symmetry, as we said, are there. There is no external drive, and we're just recently working out finite temperature contribution associated to this effect. Here I will focus on the vacuum state. So there is no phonon angular momentum, and they are not even really phonons. And sorry, I will just forgive me for introducing maybe too many formulas, but just to give you an idea, especially if you have been working with the phonon angular momentum, I just want to show you that we are not doing something funny in how we define it. So we really start from this simple Hamiltonian, and here when you write down the phonon angular momentum, you will find what we have the number conserving terms, meaning terms in which you have a dagger and A, and not a dagger or AA, so not anomalous terms. And there is always a fast oscillating component that encodes anomalous terms. But since most of the works that have been addressed up to now, phonon angular momentum, have been focusing really on this quantity rather than the 2-point correlation associated with it, these terms are well justifiably neglected because they're just fast oscillating. So if you take this expression, you will see that when you compute an expectation value, the only terms that contribute are this one, and here the expectation value will be nothing but weighting the amount of angular momentum that is present in each mode with the thermal occupation of this mode, and also some 0-point correction. So time reversal symmetry will tell us that this quantity is equal to 0, and PT symmetry, meaning inversion and time reversal symmetry, will also tell us that not only this quantity is zero, but this angular momentum associated with a given phonon mode has to vanish as well. So what we did next was to define a phonon angular momentum susceptibility, really in analogy with how spin susceptibility or other type of susceptibility have been defined. And it's nothing by this quantity. And we first focus on calculating the expectation value of this quantity on the vacuum state. And what we really expected at first was to simply find this to be zero. There is no angular momentum, there are no phonons. As for the most, I would say, intuitive expectation is that it vanishes. But what we found is that due to the presence of this number non-conserving term, the susceptibility does not vanish. And maybe something that I really would like to stress is that if you move to finite temperature, where you can still not have any notion of phonon angular momentum, you don't even need these anomalous terms to find a finite temperature susceptibility. So while these anomalous terms gives us a result that is finite when looking at the vacuum, this phenomenon is present and is actually associated with some transport effects that have been reported recently. So the susceptibility takes this form. Now, really the main, the important thing about this formula is to realize that the susceptibility is going to vanish if you have two degenerate modes, but it's not going to vanish if your modes are non-degenerate. So what does this mean? So if I, for example, consider a 3D highly symmetric crystal and I focus on the two transverse acoustic modes, you know very well that I can combine them in a linear combination that express a circularly polarized mode that precesses counterclockwise or clockwise. And this type of modes have also a very well-defined phonon angular momentum. So if that was the case, you would not find any vacuum phonon angular momentum fluctuations. And one way to understand this is that those type of modes, these circularly polarized phononic modes, they're always eigenmodes of the angular momentum operator. And now if they're also eigenmodes of your Hamiltonian, this means that the Hamiltonian and the angular momentum operator are sharing a common set of eigenmodes, and therefore they commute, right? So, and I will show this in more details later. But as you can see, we calculated this commutation relation, and we really saw that it's the non-commutativity between the angular momentum and the Hamiltonian that leads to the presence of these vacuum fluctuations. Now, another way to understand this formula intuitively, aside from this condition on degeneracy or not, is to think about it from the point of view of a two-level system that is coupled with angular momentum fluctuations. So I can imagine some quantum impurity that can couple with this type of noise. And now, when the quantum impurity undergoes spontaneous emission, it will generate some phonons according to the response function that we calculated. So here what happens if you really look closely at this response function is that the only process that is allowed is the creation of two phononic modes that belong to different branches, so one longitudinal and one transverse. And they also, by conservation of linear momentum, they have to appear with equal but opposite linear momentum, very similar to processes of parametric pumping. And they also have orthogonal linear polarization. So now the question is, how, in the moment in which you generated these modes, why the generation of two linearly polarized phonon modes can correspond to fluctuations of the angular momentum operator. And sorry, maybe I should have made this more clear. This is obviously implicit in this relation, right? If the Hamiltonian and the angular momentum do not commute, it means that by virtue of the Heisenberg equation of motion, I can have an instantaneous angular momentum that is different from zero. So we found that it was easier to understand this type of phenomenon by thinking about a classical analogy. So if you want to describe this generation of this phonon pair in terms of a classical analogy, what you can think of are two classical waves that are decoupled at time zero, and then they generate a superposition. Now, if you want to write down this classical superposition by thinking about the constraints of the quantum process, this is the type of classical superposition that you would write. Because if you look very closely at that expression, you will see that the longitudinal, since you have to create this longitudinal and acoustic phonon modes at opposite but equal in magnitude linear momentum, then your longitudinal mode by definition will always have higher energy, right? It's just what the dispersion is telling you. But if you look at this shift in energy that will come about in this factor, you can see that now this energy shift is really providing you a phase that is modulating the instantaneous ellipticity of the displacement field. And in the moment in which you assume that the two phonon modes are degenerate, this effect disappears completely. So if you look more at this classical analogy, what you see is that over a period that is determined by the characteristic frequency of the system, you will generate a instantaneously finite phonon angular momentum. But obviously this phonon angular momentum, because of the presence of time reversal symmetry in the system, has to average to zero over longer times, and already again over a period. However, the fact that it has to average to zero does not immediately imply that it cannot be finite instantaneously. And so with this, let me try to conclude this part. And it's definitely something that we are still working on. What we found is that the vacuum of an inversion and time reversal symmetric crystal can exhibit phonon angular momentum fluctuation. Now, one key to this process is the lack of mode degeneracy, but this is a very something that is satisfied practically by every crystal. And one, I would say, clear way to understand this mathematically is to realize that the angular momentum operator and the Hamiltonian do not commute. In other words, this operator is not conserved, and this is also the source of this phonon Hall effects that have been reported a few years ago. And it can also be understood maybe in a simpler way through a classical analogy. Now the question is, whether we can measure this type of angular momentum noise. And what our response theory tells us is that if we have a probe that couples bilinearly to phonon operators, this probe could potentially be able to generate and also detect this phenomenon. I've been talking about optical phonons, I've been talking about acoustic phonons, but most likely it's easier to realize vacuum condition when addressing instead the optical phonons, just because we don't need cryogenic temperatures. And while we haven't really yet discussed this at length with experimentalists, maybe Raman could be a potential technique to measure this correlation. And in this respect, there is still, I would say, a lot to do. So what we are focusing now is to understand how this the role that these fluctuations are playing in transport, and in general the role of how these fluctuations are actually connected to the really structure and quantum metric of these phononic states. So with this, I really want to thank you for the attention, and yeah, for the patients in seeing this talk online.